get started. Okay, thank you everyone for joining us in the early morning. So it's my pleasure to introduce our speaker, Dr. Rohit Chatterjee, who's also my personal friend, and he's currently a postdoctoral researcher at National University of Singapore, and he obtained his PhD degree in the same lab as me at Stony Brook University, and he also holds a master degree and a bachelor degree both in mathematics, and both are from Indian Institute of Science. Yeah. His current research interests includes post-quantum and quantum cryptography with various kinds of proof system and the foundations of post-quantum hardness assumptions. Today he's going to sharing with us his new work published at Stock this year on unclonable proof systems. So yeah, with that, stage is yours. So
thanks everyone. Okay. Great. Lovely to see you all. I'm very happy to be here at CUHK in Hong Kong. Thank you for showing up. And I'm happy to go as fast or as slow as you like. I just want to convey some of the ideas that we used in our work. So please speak up at any time. Ask me any questions you want. Let's get started. Okay, so our work is called Unclonable States Are Necessary as Proofs and Advice. And I'll explain what all of these things mean. In talking about unclonability, in quantum computing, we mean a very specific thing, and it really starts with what we call the non-cloning theorem, right? Which is this folklore thing that you learn in Quantum 101, which says that, you know, if you are given some unclonable quantum state on some quantum computer, there is no one algorithm that's going to give you multiple copies of that state without knowing anything more about it. And this is simply because of the fact that any such mapping from one state into two states is going to be nonlinear, right? So you cannot carry it out as a valid quantum map. And we know extensions of this kind of result. So for example, Werner in 98 showed that if you're taking hard random states, then the chance of you creating multiple copies of this kind of state goes down with the number of copies you want to create. It's actually exponentially low. So this is hard to do. But we know even further extensions, which is like we have specialized families of states that can be shown to be unclonable, which means that given any sort of one copy of such a state from such a family, I cannot create multiple copies. So what do we know? Here we have things called binary phase states, where basically there's some hidden function, usually a random function in the phase, and you get a superposition over all inputs to it. Or the so-called Wiesner states, which are useful in many areas, including quantum key distribution, and you know, we know unclonability for these things. And one nice benefit is that these results are really information theoretic. So this is not a complexity theoretic phenomenon. This is really something that happens with quantum computing at its core, and that's nice to know. But is it useful to know? Well, my interest into it really came in with unclonable cryptography, so-called unclonable cryptography, because it turns out that if you have this property of unclonability, this is actually kind of useful in doing some kinds of distributed computation tasks. What do I mean? Well, you can cook up examples of things that are classically impossible to do, but if you have this property of unclonability, suddenly you can do these things. And this is true because, you know, any classical information on a classical computer is trivially clonable. If I give you a password, you can make 5 copies of that password and sell it to your friends. Right? But this, in some circumstances, is something you cannot do if you have quantum data. So examples of this include the idea of quantum money, where basically your currency, your digital currency or a banknote is a quantum state of some sort. And so you get over the idea of double spending or just rapidly printing whatever money you have to make it, you know, a larger amount. And many kinds of quantum cryptographic primitives, which includes unclonable encryption, the idea of unclonable decryption, you have unclonable commitments, unclonable proofs, and variants thereof. You have things with certified deletion and other kinds of sort of primitives that build upon these ideas, and that are really not possible in the classical world. And this has inspired a whole host of literature. You also have quantum copy protection, which is this idea of like obfuscation. You take a program that runs on a computer and you make it uncopyable. So, you know, a valid user may be able to run such a program, but they will not be able to copy it. And you have a related idea which is slightly weaker called secure software leasing, and other things, like I said, that build upon this basic notion of unclonability and give you other stronger properties like quantum lightning, one-shot signatures, and like many others. Well, that's interesting, but today what I'm going to talk about is, it's useful for cryptography. It's useful for tasks where you have secrecy as default, but is it useful for computation itself? By which I mean, is there a complexity theoretic task or a problem I can solve that sort of inherently requires unclonable quantum states, right? Which means that I should be able to do a task with an unclonable state and not be able to do it otherwise. And where can you put in quantum states or quantum data, or in general, information like a string or data into complexity theoretic phenomenon? It's either, witnesses or proofs, as we call them, or, non-informed advice. So really, we start there. We start with this natural idea, and we are able to show these things. So our results include, so all our results, or at least most of our results, will be in the quantum oracle model. So our first result says that there is a quantum oracle and a language with respect to this oracle, such that this language can be decided by some quantum polynomial time verifier given unclonable state as certificate or a proof, right? And you assume access to the quantum oracle. We have a similar result where there's some quantum polynomial time decider that decides a language only with respect to some unclonable quantum advice, again with respect to an oracle. And finally, there is one interesting result where we are able to move away from any oracle and find a relational problem, which I will tell you about later, which can only be exactly solved by some quantum polynomial time decider with unclonable quantum state as advice. And this is remarkable because in several of these results, in complexity theory, it's very hard usually to find results without oracles. So oracles usually come into the picture. And the third result is remarkable in the sense that, there is no oracle here. So this is just the background. So I'll pause for a second for any questions you may have. Okay, so let's dive into what we mean by quantum proofs. Right, we're going to be talking about this class called QMA, which is a quantum generalization of NP. So think of it as this way. There's two parties. There's Arthur, the boy with the sword, who has some instance to decide, and Arthur will be computationally bounded. There's Merlin, who's computationally unbounded, who also knows X, and he's trying to help Arthur decide. Yeah. So you have some input. You're trying to see if it's in the language. What do you do? The challenge or the condition for Arthur to win is basically, if the instance is in the language, you say yes with high probability. If the instance is not in the language, you say no with high probability. In QMA in particular, both of these machines are going to be quantum computers. Arthur is still polynomially bounded, and what Merlin does is sends a quantum state as his proof or witness. This is the class. You have a very closely related class where everything else is the same, except Merlin is now constrained to send only a classical string to Arthur. Okay, so in QMA you send quantum proof. In QCMA you send a classical proof. That's the only difference. It seems very interesting. So now you're trying to learn about quantum computers. You want to sort of gauge the class of languages these things can decide. And so in that sense, you want to say, well, does the nature of the proof play a role? In particular, do we want it to be quantum? And how do we decide that? We say, are these classes equal? And this is interesting because it's one of the fundamental open problems in a particular branch of quantum complexity theory. People really care deeply about this problem. And it turns out that it is hard to solve, even separating these classes. So we believe these classes to not be equal, like NP and P. And we want to separate these classes, but people have so far only been able to do it with respect to oracles, and in particular, actually, mostly quantum oracles. So by oracle here, the classical notion of oracle is clear to everyone. The quantum notion of an oracle is kind of interesting. You just define one unitary for each input length, because you can't sort of capture all possible input languages like in the classical case. Anyway, quantum oracle separations between QMA and QCMA are known. The first one was by Aaronson and Cooperberg in 2007, and there have been follow-up results. Interesting enough, this is a very hot topic in complexity theory right now. over the last 2 years, people have been trying really hard to get to a classical oracle separation in some form or the other. And all of these results are classical oracle separations with some particular caveat that may or may not apply. The most recent ones are interesting in the sense that they make some sort of cryptographic or statistical conjecture with respect to which they can show a classical oracle separation. But we don't have a complete classical oracle separation yet, but we are very, very close. And why do we care? We care in the sense that if we show some class of languages which have unclonable proofs, which inherently require unclonable proofs, that helps separate these two classes. How? Well, classical proofs are always clonable, right? So if a proof is unclonable, that means it's inherently sort of quantum. And so you have a language that, is in QMA but not in QCMA, and you get the thing, and this is meaningful with respect to the oracles as well. Right? And in particular, we will care about this because we'll use the original oracle from Aaronson and Cooperberg to show our result.
So at this moment, I think it's important to define the exact requirement for unclonable proof.
We will get into the, yes.
If I say a language is admit an unclonable quantum proof, that means it can only be proven using unclonable quantum proof, but it's not.
That is exactly the heart of the definition. We'll get into that, yes. Yeah, so similarly, what is quantum advice? Here we don't really need a diagram. You just have a quantum polynomial time decider that gets this advice. So you have classes BQP over qpoly, where the advice is a quantum state, and BQP over poly, where the machine is still quantum, but you still have classical advice, right? And we're trying to see if these classes are equal in the same sense. And two caveats about advice, we didn't get into one of them. One is that it depends only on the input size, which we covered. The other is advice is always there to help you. It's always trusted. You don't have to worry about where the advice comes from. And so it's just a simplifying assumption in some sense. These things are actually quite related to the QMA QCMA question, and this has been observed before in previous works. And one related thing that comes into our third result is this quite recent result by Aaronson, Buhrman, and Kretschmer from 2023, where they show that relational versions of BQP over qpoly and BQP over poly can be unconditionally separated without an oracle. And this is quite rare. And it's a very, very cool result. Relational versions of these classes are sort of defined in the sense of, like, you have FP with respect to P, where you're supposed to compute a function instead of deciding whether some input is in a language, a 0-1 response. You have to output some number instead. And similarly, in BQP over poly, you're given a quantum polynomial time machine with advice, and it has to compute some particular function you want, some particular deterministic function. And this is very, very interesting. And like I said, you can define FBQP over qpoly for these relations, where you're not just outputting 0-1, but some larger response. And one thing to point out is that the construction by Aaronson and others separates the class FEQP over qpoly and FBQP over poly. And this is important because we'll be really working with this class. Our result will not go up to FBQP over qpoly, but the separation still burns, and we will build on their ideas. So that's background about quantum proofs and quantum advice. So once again, I'll pause for questions. Okay, let's keep going. What is unclonable proof or advice? So let's take a first attempt at defining what this is, and then we will turn to unclonable languages. This has been considered in a couple of previous works, actually, and people have been trying to get at a good definition. So cloning means I have to create multiple copies of this proof or advice. How do we imagine this? Let's say there is a proof, for valid proof for some instance with respect to some language. You're giving it to a cloner who knows the instance, right? And the cloner's goal is to sort of create multiple copies. Let's say at least 2 copies. So let's say you have 2 independent verifiers that want to decide this instance, and the cloner passes something to some of them, right? So A passes a state to B, it passes state to C, and then B and C independently attempt to verify the same instance. And if they succeed, then the cloner can be said to have successfully cloned the proof. So this is the setup. Similarly, in the case of advice, now you get one state for every length of input. The cloner takes in this advice and provides some cloned advice to B and C. They get their own independent instances to decide and produce a decision. Now you want to see how well they do.
So in this case, there's no input x. Your x1 and x2s are advices.
They are instances. Yeah. So the cloner, like in the case of advice, there's no meaningful sense in which the cloner can know the instance. Yes.
So the cloner doesn't know which concrete instance will appear later.
Yeah, it's just trying to clone the advice because that's more fair, right? Okay, so one thing to point out here is that the functionality of the state is the thing that you need to clone. So what I mean is that, of course, it is possible to succeed in this task if you directly clone psi x. But you may not need to do that, In particular, cloner can, of course, produce two copies and it helps them with the proof, but it can equally well produce some joint state across joint registers of B and C. And that can help them work, that can help them decide properly. So you're doing something more strong, more general than just disallowing. If I want to say that this cannot be done, I'm doing something more general than just saying psi x cannot be cloned. I'm saying psi x cannot be used to create anything useful that helps B and C succeed in deciding the language. And this will win.
Fine. Your assumption is B and C cannot communicate, right?
B and C cannot communicate.
Can I repeat what you just said?
I said while B and C cannot communicate, they may have a joint register on which A might produce joint state. They're still not talking to each other.
So
and then they might win, right? So it's not.
So why? They are not communicating. They cannot even do things like teleportation.
Yes, that's fine. But it's. I'm saying the winning state does not need to be two copies of psi x.
Oh, that's fair. Yeah, that's fair. But I don't think this is because if they cannot communicate, even if they hope it can go, still it doesn't transfer any information.
Yes.
This is something you can prove information directly.
Yes. So that's fine. Yeah. So I'm not saying that. Yeah, this picture may be slightly misleading in that sense. Yeah. And another thing to note here is that the cloner must also be computationally bounded. Otherwise, it can just do what Merlin does. And B and C, of course, naturally computationally bounded. So that's the rough idea of clonability I want to use. Next, we will turn to the definition for unclonable languages. Everything clear? Oh yeah, one thing we want to consider is sometimes average case unclonability is also useful and may be important for cryptographic applications. Here we are only dealing with worst case unclonability for now. So yeah, so as Zhao pointed out, this is talking about really when a proof system is clonable or unclonable. We want to define languages which have only unclonable proof systems. So how do we do that? And this is not trivial to do, right? So this is the requirement we have in mind. And the question is, can we always do this, given that we find one proof system for a language that's unclonable, does that mean, we get a language of this kind? And no, because, you can have some classical canonical proof system which has unclonable proofs, but you can equally well define a contrived proof system which uses two copies of the same proof, just doesn't look at the other one, and now this is trivially clonable because the cloner knows this and can use both of the copies to clone. So this it's not a property of the proof system is what I'm trying to get at. So instead, what can we do? We use this idea. So you're given some polynomial size family of proofs. You have bound on the size of the proof. It can contain two proofs, three proofs, many proofs of this kind. How many proofs can it have? It can have at most polynomially many copies of some smaller proof. And that's the idea we're trying to use. So you're saying you cannot say stop at 3. I cannot create 3 copies of a proof. That's untenable to do. You cannot define something like that. Instead, what you define is that any family of proofs, I will give you a polynomial for which cloning will not be possible. Right? So this is just quantification. That's all.
So when you say for any polynomial set on the proofs,
yes,
should I think it as for all language or for all instance in a certain language? I mean, I'm more used to the notion of language. Or
as it turns out, our instances will be very trivial. So I think the second definition is nicer. but it does not seem to make a difference for us.
So I just want to know,
Yes.
okay, is universal for a language or for a class, or it's for like for each different instance X you need to okay.
Yeah. So I think the way we have defined it, it's for each instance, but in our language, it's kind of the instance does not play an important part, so it will actually achieve.
I think your case like maybe it's a protocol specific for each protocol in the function.
Yeah. So the protocol comes with the proof system. Sorry, with the proof family.
Yeah, but if it depend on the protocol,
Yes.
it doesn't necessarily need to depend on the instance. Right? Your protocol can work for everything.
Yeah, that's what I'd like to believe. It hasn't come out in the course of like I haven't illustrated this property well.
Yeah, I just want to know when you say a family of proof, what does that mean?
Right,
I
right.
should think it as a protocol, family protocol.
Yes, I think that is yeah. I'm forgetting the exact definition, but I think that is what it is. Yes. Okay. So it turns out that we can work with this. And we preserve the property that this disallows classical proofs, because classical proofs I cannot define any such k because I can just keep cloning for classical proof. Oops. And one good thing about this kind of definition is that the unclonability is still worst case, which is usually considered nicer for complexity theoretic tasks. So I will illustrate this. So strictly unclonable QMA and FEQP over qpoly are defined as follows. Strictly unclonable QMA is of course a subset of QMA. You have some, let's say, polynomial family of proofs. These go to a cloner. I'm saying then I can define some k, which is polynomial over size of the proof, such that you have verifiers b1 through bk, and A cannot produce some joint state for all of b1 through bk that helps them decide the language. So these should not be jointly correct with high probability. And this is in some sense just the correctness definition. I haven't given the soundness definition. But this is just to give you a flavor of how we are defining these things. And you can define these things with respect to some oracle, which we will be doing. So then
all of these are still non-communicating.
Yes, that's important. Yeah, and then everything has access to this oracle. And the proof state may also depend on the oracle. Similarly, for FEQP over strictly unclonable poly, we define it as follows. You have some.
I think it's clear for companies, but for some, it's when X is false, you want all of them operable or just one of them.
So we define something called joint soundness. So I think all of them output no, because I think one of them output no you can still achieve by not cloning.
I see.
Yeah. So for FEQP over poly, you have advice state. And again, I'm defining some large polynomial such that, b1 through bk cannot decide this, cannot give me an output that satisfies the relation, because this is the relational class, with probability 1, because this is FEQP instead of FBQP. And this is because technical restrictions in our proof. These are roughly the classes. And again, I will pause for questions about the definition.
No question, but the common I still found is confusing to think that it has your K depend on protocol. It's not the nature of the class, right? So for example, when you say K here, you have to talk about protocol first.
Correct. But I'm saying there's a K for every protocol for the language, right? Which is.
That means if I design a new protocol, I'm gonna define a new class.
Yes. Oh, new K, not new class, but
once you have a new K, you have. I think there's some hierarchy.
Hierarchy in K. I see. That's interesting. It quantifies how strong my unclonability is. That's true. So yeah, let's turn to our constructions. I will describe some more of them in more detail, but this is just to give you a flavor. For strictly unclonable QMA, we will use the Aaronson-Kuperberg oracle problem, which they call quantum OR. The names are weird, don't worry about it. And the idea here is, given an oracle that is either reflecting about some unknown hard random state that you don't know. You have to decide whether the oracle that you're given is either the identity throughout or is actually this reflection oracle. And the instance is kind of a dummy instance. There's no instance really. So this is why this is weird. And the proof that works really is the state psi itself about which you're reflecting, right? And this is good starting point because such states are unclonable, like I pointed out before. And that's how it works. For FEQP over SU-poly, you have to consider this problem called hidden matching, which is used in quantum communication complexity sometimes. And here, basically, this is indexed by some predicate, by some Boolean function. And you have this strange relationship where basically you want to test whether given some input y to the function and some value b, you want to check if there's some shift x such that f of y XOR with f of y shifted by x gives you this value b. It was originally inspired by some graph theoretic problem, which is why it's called hidden matching.
This one doesn't have oracle.
Yes, that's the cool thing. You're using some fact about
B is just a B is binary.
yeah, B is binary. The advice here turns out to be some binary phase state that works. And you know, these for random functions are known to be unclonable. So again, it's a good starting point.
For the first problem,
yes,
I missed why the state psi is
we will. I'll describe that actually. I think I will draw it up.
Oh, I think you're gonna skip that.
Let's see. Yeah, no, I'll can't do that. So we'll go through these two things mainly. So general proof strategy, very briefly. You want to show rigidity of the proof or advice, by which I mean we're solving some decision problem, right? So at the end, B1 through Bk will give you 0, 1 answers. How do I use unclonability? There's no copies of the state being created. So the first step is to really show that, you know, if I can have a cloner and multiple verifiers that succeed in solving the task, I can, with some extra computation and some extra queries to the oracle, produce many copies of the original proof state, right? So that gives you some unclonability task to refute. And
now you're proving this is the unclonable proof system.
I want to prove that these candidate constructions are unclonable proof and advice systems. Yes.
So I think I am talking about protocol. So for the first one, are you already defined the protocol?
The protocol, let's say, is this. So, oh no, I haven't defined the protocol. We'll come to it.
Then
I'm defining the language, right? The language is what I care about.
But you define it in like QMA fashion, which means
yes. So I'll show you how the natural proof works for the natural verifier.
Yeah, I want to see what the syntax of a natural verifier on the.
Okay. Yes.
So the natural verifier take the witness as input.
Yes.
Query oracle.
Yes, it will make a query to the oracle. It just does some controlled operation. It's not too.
If you give verifiers this slide,
Mm-hmm.
when you query the oracle, let's say we are in the first case.
Yes.
The reflection about psi.
Yes.
It's gonna return psi itself, right?
It's gonna return minus psi, right?
No, that's to give psi part. Is that the type of thing?
No, it's 1 minus 2 psi psi, right? So it will give you minus psi.
1 minus 2 psi is a reflection about psi, right?
Oh, sorry. Yeah. So yeah, you're right.
Yeah, psi part. That's what I'm confused.
Oh, okay. So it's some trick that people do. You'll see it. It's very clear.
But are you claiming psi is a proof or psi part is a proof?
Psi is a proof.
Then it behaves the same for the two oracles, right? If you feed it to identity oracle.
Yeah, but you can build some other state that that will behave differently. Like if you add some plus state to it.
That means your verifier is doing something extra. It's not simply querying the oracle.
That's correct. I didn't say it. Yes.
Yeah. Then can you first describe the.
Okay. Give me a slide. Yeah. Yeah. Sure. Okay. Okay, let's start here, and I'll go. The general strategy doesn't matter so much. Okay. So, like I said, the instance is kind of a dummy instance. You have this oracle, and you want to know whether it is either this reflection oracle or an identity oracle. the proof is this. How does this work? You sort of add a plus qubit before psi and apply the oracle in controlled form, which means like, apply the oracle when the first qubit is 1, otherwise you don't.
Wait. If you are given the oracle,
Yeah,
it's a quantum oracle, right?
yeah.
You cannot use it in the complement.
Yeah, so this is true, but there's some argument which I didn't want to get into here for why this is
So
okay.
did you get rid of this problem, or you actually assume the like control oracle?
Yeah, the people who use this protocol before us assume that you can get this.
Control oracle.
Yeah. Let's say for now it is controlled oracle. There's some very new exciting result by Evan Tang that says usually you can go back and forth also in general.
They can't get rid of the control oracle.
In general for quantum problems. But in this case, these are equivalent as argued by Aaronson. Yeah. So if you have the control oracle, you do this and then you measure the first qubit of the result in Hadamard basis. And then note that if this is psi and you run the control operation, you will actually get the minus state now. So you just have to measure that and see it. Your psi is preserved and the verifier accepts with probability 1.
So you control on this extra
Plus.
plus.
Yes.
Okay.
Yeah, that's so the verifier is doing this controlled computation and one oracle call. That's it. And this seems pretty sound that if you have anything else, really something will go haywire and you won't get psi minus with probability 1. And we will want to ensure that sort of the role of psi here is what is not cloned freely. So let's get into that. Recall that for strict unclonable definition, we consider the problem in the k verifier settings. There's multiple verifiers, and each of them solves the decision problem. So we can again only use unclonability if we produce some copies of psi at the end, right? So the key idea here is that we want to say that any such cloner verifier system that can jointly solve quantum OR in the k verifier setting can be modified into a system of different cloner, different verifiers that instead outputs something very close to k copies of psi onto some joint register with only polynomial more queries and more computation. This uses the a hybrid method and fixed point quantum search. It's an interesting idea. It's not very new. My co-authors certainly thought of it as a standard technique. But
do you need to make k to k plus 1?
I'm going k minus 1 to k here implicitly.
That's another. Okay.
Yes.
So you start with k minus 1.
Yeah. Let's say, I can't start directly with k minus 1, which is the next problem I'll come to. Okay, so this can be done. You can produce, if you can solve the decision problem, you can produce many copies of psi, starting from whatever advice state. And the extension is this was known for one verifier. You can do it now for multiple verifiers. That's fine. What is the unclonability requirement? And this gets to what Zhao spoke about. We know how random states are unclonable. That's good. We have an oracle, which is bad. So now this can potentially compromise unclonability, right? We are getting extra information about the state. The good thing is Aaronson and Cristiano in another work showed that Haar states are unclonable even given this oracle, which they used to show quantum money. However, our nature is somewhat different. So what is different in our case is that unclonability results exactly guarantee hardness of creating psi k from psi k minus 1, right? K minus 1 copies of psi. So less copies to more copies. But it has to be less copies that you start with, which is not the case. We are starting from some arbitrary polynomial-sized proof state. How do we deal with this? So this is basically the key of this particular result. And we will get into this.
Well, I won't really explain the ugly part. I don't get it.
So it's like this, right? So even something like Aaronson and Cristiano showed it holds again if you start from psi k minus 1 or less to psi k. But we're not doing that. We're starting from some arbitrary, we are taking some arbitrary. So what I showed you is the canonical.
In advance or not?
You know k in advance. So I will define k. And so I will see so this works as follows. In the overall proof, I will take in some proof system. I will look at its proof size, and then I will define K.
Yeah.
And I will show you how to set K in the next slide.
You are saying it's hard to infer K from the proof system?
There is some direct computation. It's not trivial, but there is some number you can calculate.
Yeah, but why this doesn't why this isn't compatible with Aaronson this channel?
Oh, because they're saying they're only sort of handling one proof system, which is the one that takes in K-1 things.
But it's for general K, right? For any K.
But you don't know, like it could be some random state, right? It could be some, it could not be some product state, some nice thing here. It could be some completely arbitrary polynomial time state, and that's what you have to show. And if you don't start from that, you cannot use this result.
So I think AC works for some specific K, not for arbitrary K.
No, it works for any K-1 to K, but the problem in our setting is you may not start from, like the advice state that works, it may not be K-1 copies of psi. It may not be one copy of psi. It may be some weird state that does not look like psi at all.
Oh, you
Yes.
think like if you consider joint state over all the B's, you cannot say explicitly, okay, they are just a tensor product of K-1.
Yeah, and that's about the output of A. The input of A is also unclear, right? You are given some arbitrary proof family, so you don't know what it looks like.
I see.
And so,
I see.
yeah, so we have to deal with the uncertainty in the proof state, and we also have to deal with the oracle. So let's turn to these two problems. And I think I'm happy to show this and end also. So let's take our time with this. So we want to show that given any polynomial time proof family, there does not exist any efficient cloner plus k verifier system that produces, k many copies of psi. The starting state may be arbitrary, so I've called it Fi. And let's not worry about the number here for now, it plays some role. Okay, so our approach is to use something called spherical K designs for some reason. I will explain in a second. For carefully chosen K, and just to show there's an explicit number you can compute for K, which is basically you take in the.
That should be cloner plus K minus 1 verifier.
Oh, no, because the K verifiers are the one. The cloner just takes in the proof state and applies some map. The verifiers are the one who decide.
Yeah, but I think in this proof, somehow you need to jump from K minus 1 to K, right?
Yes.
Where is the K minus 1? I don't see.
Yeah. So we are not, like, we don't even need that. So this is more general than just saying ruling out K-1 to K. I'm saying I will start from any polynomial size family Fi.
Yeah.
I'll define some K such that you can produce K.
There doesn't exist.
Yeah.
I think I don't understand this. Otherwise, it's for example, okay, if I set K equals 1.
Yes. You cannot, right? So
you qualify over for all polynomials.
Oh, I haven't. I see. Oh, I mean, this is inside brackets. So there does not exist this thing that produces psi k for all polynomial k.
Maybe can explain it in like plain English what that.
So I'm saying they're given some proof family.
Yeah, I think that's basically you include the adversary if that is a family.
No,
I'm sure you need to handle the problem that if a system can generate K-1 proof, then you cannot like generate one more proof in that tree.
Yes, so this is captured by this. So I'm saying there does not exist any efficient cloner plus k verify system that produces k copies of any k copies of phi, any polynomial many copies. It's saying you tap out at some k.
Oh, okay.
You'll get for limited k, you won't get this system that works for all k.
So basically, you're saying there exists some k that
yes.
you cannot do.
Yeah. I haven't said it in that way, but yeah. Okay. So there's actually some technical relationship. So you have to take in the symmetric K-1 size subset over n qubit states. and you set the log of the dimension to be larger than the size of the proof states.
So can I understand the intuition of this proof as once you have a bounded number of qubits, it can only encode the bounded number of information, so you cannot generate.
That's good to say. Actually, you can understand it more precisely, I hope. So what we will show if this K is chosen carefully is, and we use these spherical K designs, is that the optimal, take the best clone you can imagine, and this is just going to apply some map to your Fi and then project it onto K copies of psi. What it can do, if you start with the setup, is effectively try to learn I by acting some measurement on the proof state. You can show this, and by our choice of K, the Fi's have like some very low effective dimension. Like you can show they belong in some subspace with some very low dimension. And on the other hand, there are many of these states. And that means these two facts taken together mean that, if you try to learn I by a projective measurement, not projective, any more general measurement, then you will only succeed with exponential probability when you also average over I, right? So when you pick some Fi at random and you try to do this task, you will not really succeed. And so you get the conclusion really that you wanted. So you start with some polynomial-sized family proof system. This is one part of the thing. There is no possibly unbounded cloning procedure that maps Fi to K copies of psi with more than negligible probability. So this is the core of the result, yeah, and it's a generalization of Werner's unclonability proof for hard random states.
Did you use any like quantum entropy notion in this argument?
No, not
Do you
really.
have an intuition why?
Somehow, like where would you use it? I guess the entropy thing sort of plays part here. Like I don't know how to make that entropy argument, but I think whatever notion you use.
Also in this way,
yeah.
So this kind of proof a natural technical tool to use would be entropy because you are talking about how many information.
Yeah. So in fact, for the advice part of this thing, so when you separate BQP, when you show BQP with unclonable states, we use an entropy argument.
Yeah, but in this one, what would be the main workhorse in your opinion? What is the tool you use?
Yeah, it's this. It's Werner's original proof, which says something similar, where you can argue about some unbounded cloner that does something, and apply this kind of structure to it, and we are generalizing that argument in some sense.
So, this proof come from whose paper is it? This technique.
A. Werner, yeah, Werner 98. It was unclonability of.
Werner doesn't give proof. You know that? He just
So my
give, yeah, he just give like a 10-page paper without the proof.
Yeah, there's some other horrible paper which uses some nasty calculus to get this.
I see. Probably you're saying, this kind of thing, this structure
Yeah.
works, but the why it works. If you want to prove it works, you need to talk about entropy.
It does not come up actually. So you can follow our proof. It's quite simple. Like it's not very complicated. So it will give you exactly the same thing. It's not too bad.
I see. Okay.
Yeah. Yeah. So, but we haven't handled the oracle. How do we handle the oracle? We will use a trick that is known. So first, we will show that there is some subspace of half the dimension of the overall space, such that our special state size here. And you cannot distinguish between oracles to either the special state or a reflection oracle for this whole subspace S with polynomial mini-queries. This is some well-known result that's often used in this kind of query complexity results. And you can simply then replace the reflection oracle with the reflection oracle about S. So that's the first step. The second step is S is now some subspace. So earlier, the issue was if you can always also compute u psi using psi, right? If you know psi, you know u psi. That's not a problem. But if you describe u psi using psi, there's no hidden thing about psi. Everybody can compute psi. So that's not good. But however, now you can give out S to replace us. So instead of providing Oracle access to US, you just give the potential cloner S. It still sort of information theoretically hides psi, but the Oracle can now perform its but the cloner can now perform its Oracle queries on its own. In the process, it becomes inefficient, but we don't care about that because our earlier result handles inefficient cloners. What is the issue? Now your reflection Oracle is going to reflect a lot more things. This can be bad, right? But you can sort of do a more limited reduction. So we are effectively saying that producing key copies of some psi which belongs to some random subspace of dimension 2 to the n over 2 is equivalent to producing key copies of an arbitrary n over 2 qubit state. So half the size of the original proofs, because S is random. So these two things are effectively equivalent. And you reduce size in your reduction to appropriate parameters, but it still goes through. You just have to scale up k accordingly and so on. That's it. So how are we doing on time? I also have more complicated proof for the FEQP result, but I'm happy to skip that. Okay. Okay. So let me give you some. So first, questions about this whole procedure. This gives us our unclonable QMA result. Okay. Let's look at hidden matching briefly. So here, different setup. So this original separation, FEQP over qpoly versus FBQP over poly, uses this result, this separation in quantum versus classical one-way communication complexity, which I want to show you so that you can maybe read about it later. It's very cool. Here the setup is basically you have some two-party relation. So you have party one's input, party two's input, and some output. Alice and Bob. Alice here sends a message to Bob, and the one-way communication complexity setting, only Alice can send messages to Bob. There's no backwards communication. So one message to Bob, Bob then uses its own input and the message to compute some response, and you want to test whether it's an A. And the task is, of course, for any particular well-defined problem of this kind, how many bits or qubits do you need? And if you use this particular hidden matching problem, which I showed you earlier, you have this F, you have this shift X. You want to find a Y such that, F of Y X or F of Y shift equals some value. How many bits do you need to solve this hidden matching problem? Here, Alice has the function and Bob has this X. So Alice's input is much larger, actually. It turns out, in the quantum case, you can send this sort of phase state. And Bob can do some clever calculations to sort of get basically a superposition over this kind of states and compute some value. And it will be correct every time. So the quantum computation complexity for solving this problem exactly is just n qubits, because this state is actually n qubits. On the other hand, if you try to solve this problem classically, it can be shown that you basically can't do much better than 2 to the n over 2 bits, classical bits. This is a huge exponential separation, and this has been interesting to the quantum complexity theory people, quantum communication complexity theory people. But this result sort of found a way to harness this to establish this BQPs versus FEQP separation. One of the main results we use here is the following theorem, which sort of plays the role of a rigidity result, is that if Bob's state before outputting on inputs F and X is Bob's input, F is Alice's input, is some state, then it has sort of this structure. And I mean, this is just the output register. It might have some residue state, but it roughly looks like this. Basically, superposition over all the possible successful answers, and you have coefficients here on each Y's. And actually, you can show that these have actually quite large mean entropy, these coefficients.
Do you assume Bob is honest, or some you don't know because it's not protocol? So what do you mean by the state for outputting?
Yeah, here I'm talking about honest Bob, really, I think.
But you don't know the protocol. Your proof is obvious for protocol.
Oh, in that, sorry, so yes, so here's the,
Something like the bubble first prepare final state, the measure it under completed output the first lifestyle. In this model, I can understand what you mean, but if you don't
yeah, that's
fine.
right. So there is this thing, but it effectively happens to be the, so you can show for general Bob that Bob's outputs have high mean entropy. And there we are using, yeah, this is basically on faith that we are saying that then Bob is some classical quantum machine, and it basically measures its output. And so its state right before outputting looks like this. Yeah. Initially, I also did not like this argument, but it seems to be customary. Yes. Uh, so the original canonical advice state, which is the binary phase state, is also in this family. And this, you can also use this not for the exact computation problem, but for the binary protocol. It's not important. And really, why can we say this? Why can we say Bob's inputs have high mean entropy? You're using this sort of Yamakawa-Zhandry like idea, which is very, very cool. You're saying that actually, if this has low mean entropy, you can use some result by Aaronson earlier, where if Bob's outputs have low mean entropy, then basically you can replace this with a classical message protocol. But we just argued that the classical message protocol has extremely high communication complexity, so this can't be true. And so in this roundabout way, you argue that this has high mean entropy. That's basically what I said. And then you can build on this, and you also use the fact that these phi fx's for different f have inner product half. So this result is for one verifier. You need to move to multiple verifier settings. Here I'm rushing a bit just to get to the end. We can't really show that in the k verifier case you have product state for all the verifiers, but we can show that overall they share very high mean entropy. And then when you take inner products for these sort of different answer states, they still have low inner product, and we can use that to get our final contradiction roughly. So in spirit, this is sort of the same pathway we followed for the earlier result, but each step looks slightly different. So let's see what our constructions give us. So this is mostly about the QMA, unclonable QMA thing. We are helping separate QMA and QCMA with our particular oracle, right? Because our language sits there, it's outside of QCMA, it's in QMA. And to compare, there was this separation by Nehoran and Zhandry, who created this class called cloneableQMA, where the proofs were clonable but not telegraphable, so they were still not classical. And they use a different oracle.
Wait. I think your SUQMA by definition is there.
Yes.
You didn't give a construction without homework.
Correct. So
you didn't solve the problem, right? You didn't show.
We didn't solve the problem without oracle. We didn't solve the problem without oracle. We have only recovered the known oracle separation, you can say.
So your results, I could understand it as a new perspective of
Yes.
existing.
Or maybe as a strengthening of these separation results.
You didn't get any stronger separation results.
Correct.
Okay. Just a new perspective.
Correct. Yeah. In fact, weaker, because now we know almost classical separations, right? So anyway, so this is a different style of separation, so it's more evidence for the fact that these two classes are separate, because there's now two layers of separation in oracle models. And open problems, it would be nice to separate these things with classical oracles or just a nicer, more natural language. Seems hard, but anything is possible. We used FEQP over qpoly because of technical reasons. Can we do strictly unclonable version of FBQP over qpoly? Because this will still be a result without oracles. It turns out that we can't even define this class properly because it does not have error reduction. So for many instances, the errors look horrible and things like that. And in any case, if any techniques works, it's not going to be ours because we have fundamental challenges in ours. And finally, also, using this for quantum cryptography is one big thing that might be exciting to Zhao. I also want to use it for like more natural crypto tasks. But for now, our result is just complexity theoretic. And with that, I'll stop. Thank you for listening.
Let's first give Rohit a pause. I want to ask this because it's all about pure states. Mixed states.
Correct. Mixed states are horrible to work with, so usually people don't like to work with them. I lack the broader scope of knowledge to say what people have done, but usually complexity theorists at least like to pretend that they can purify everything and everything works.
You're talking about proof system. So for proof systems, if you allow advice, you can always purify. Yeah, if you have like a proof system that has to use a mixed state, you can always like
Right,
purify it by some polynomial extra resource. Then you can do like, use the same framework. But in that sense, I think pure state is just without loss for generality.
Yeah, but in practice, this can be actually I listened to a fascinating talk earlier this week at the AQIS conference, which talks about purification as like general purification and yes, that was quite good.
Oh yeah, what did they say?
She was looking at the purification problem, exactly how many. Debbie Leung, I think she's faculty at Toronto.
Okay.
Yes. Yeah, it should be there on the alpha. Purification problem, like exactly how many qubits. Just finding a lightweight circuit for purification in general.
Well, that's not for this kind of research. This kind of research is practical in whatever university.
Yes. So.